Hello everyone, welcome to another video on integration. In this video I would like to talk about trig substitution, and to be specific I'll be looking at the tangent substitution. Now just a little bit of the background or a background in a trig. So I'm going to just take you through a couple of things on trig that we need to know. So let's focus on the first quadrant then. Suppose you have the Cartesian plane here and there is your x-axis, your y-axis, and you're focusing on that right angle triangle, and the angle of focus is this one here. Let's call it theta, and therefore this distance from here to there, let's call it x. That vertical distance there, let's call it y, and the hypotenuse, let's call it r. By definition, we have the following trig ratios. We have sine of theta, by definition is the opposite side over the hypotenuse, and then we have cosine of theta, by definition is the adjacent side over the hypotenuse, and by definition again we have tangent of theta is the opposite side over the adjacent side. Again, I want to just put a star here. The other trig ratio we're going to look at is the secant. Sec theta, by definition, is the hypotenuse over the adjacent side. Now, let's go to page 2. I want us to look at these two, the sine and the cosine. Suppose I divide sine by cosine. Let's see what we get here. So, number one, this is critical. If I divide sine of theta by cosine of theta, what do I get? I get sine of theta divided by cosine of theta, like so. What is sine of theta? According to the first quadrant definition of sine and cosine, we have y over r and then x over r. For sine y over r, cosine x over r. So we're going to have to say here y over r divided by x over r. Let's simplify these as fractions. So we can have y over r times r over x. Remember, when the division sign changes multiplication sign, the fraction dividing is reciprocated. So r goes up and x comes down. And notice that these cancel. So finally, what do we have? We have y over x. And if you check here, the definition of tangent is just y over x. So we have now established that tangent theta is actually sine theta over cos theta. This is critical because you will see later, we'll come back to this. Now, I want to say that here the assumption is that cosine of theta is not equal to 0 because you're not allowed to divide by 0. So result 1 established. Now, I also want to look at result number 2. Let me get to page 3, result number 2, and now I want to talk about secant and cosine. Now, suppose I divide cosine into 1. I reciprocate cosine. So this is result number 2. Suppose I have 1 divided by cosine. How does it look like? Cosine of theta, like this. This is the same as 1 divided by cosine of theta. And what is cosine of theta? X over r. So this changes to 1 divided by x over r. And if you treat this as a dividing fraction, you're going to have multiplication sign here, and the fraction, that fraction reciprocates. So this is what you have. And what is 1 times r over x? The answer is r over x. And if you look at the definition of secant, it's just r over x. So now this is result number 2. We can say, therefore, secant theta is just actually 1 over cosine theta. So result number 2, very critical. Please remember this. We're going to come to this again. Right. Now, let's look at result number 3, which we are going to need. We are back in this right angle triangle here in the first quadrant. Remember, quadrant is a quarter circle. Suppose you have a circle going around like this. That would be your first quadrant. And the second quadrant would be between 90 and 180 degrees and so on. Now, while we're still in this quadrant, we understand that Pythagoras theorem, if you want to call it an item on its own, let's call it number 3 then. We understand that Pythagoras theorem says that the square of the hypotenuse is equal to the sum of the squares of the other two sides in a right angle triangle. So we are saying um, y squared plus x squared is actually equal to r squared. This is because of Pythagoras theorem. Right, this is critical because I'm moving straight to point number 4, which basically is, what do we get when we square sine theta, written as this, sine squared theta plus cos squared theta? What do we get? The understanding of this is that this is exactly sine of theta all squared plus cosine of theta all squared. And what is sine theta? This is y over r, remember? Sine theta, here it is, y over r, and we're squaring it. Plus, what is cosine of theta? It's x over r, remember? And we're squaring it. What does this give you? It gives you y squared over r squared plus x squared over r squared. Remember, when denominators are the same, what do you do with the numerators? You just add them. So y squared plus r squared all over, y squared plus x squared, y squared plus x squared all over r squared. And what is y squared plus x squared? Go back here, Pythagoras theorem up there says y squared plus x squared equals r squared. So therefore this can be written as r squared all over r squared. And what is r squared over r squared? 1. So it is item number 4, very important item, that the square of sine plus the square of cosine is always equal to 1. So that's number 4. Now we're moving on to the last one. Number 5, what I want to talk about, number 5 is, we have established now that if we let y be equal to, at least in the previous videos, I have explained to you that if y is equal to f of x divided by g of x, which we can write as y is equal to f of x all over g of x. If I want to find dy dx by quotient rule, dy dx, this is exactly equal to, you differentiate the numerator, f prime of x multiplied by the denominator, g of x, then minus, differentiate the denominator, which is g prime of x, and then multiply by f of x up there, and then we're dividing the whole of this by the square of the denominator, so g of x all squared. Let me rewrite this in a better space. I'm saying that that is exactly equal to f prime of x times g of x minus g prime of x times f of x all over the square of the denominator, g of x all squared. This is, I've explained, I've even proved this. It's called the quotient rule of derivatives or differentiation. Quotient rule, right? Now, using quotient rule, we want to differentiate tangent and see what we get. So now we're basically saying, so let y be equal to tan theta. What are we saying? We are saying that y equals sine theta over cosine theta. Remember, we proved this. Here, that let me just get the page here. We proved that sine over cosine is actually tangent. I think it must be on page number 2. Page number 2. We proved that sine over cosine equals tangent. Here it is. Sine over cosine equals tangent. Now I want us to differentiate tangent and see what we get. Here we go. By applying quotient rule, we are basically saying dy dx. Therefore, dy dx will be equal to derivative of sine. You must always remember this. It's cosine. So cosine of theta times the denominator, which is cosine of theta, minus derivative of denominator, derivative of cosine is minus sine. So remember, I'm going to write it here, minus sine theta. And then we're multiplying by the numerator, which is sine theta. Space there, I'm going to rewrite that all over cosine squared theta, written like that. Now if I stretch it backwards here because of space. I'm basically saying cosine times cosine. Let me just rewrite it. We're saying cosine theta, derivative of sine is cosine theta, multiplied by the denominator, which is cosine theta, and then minus derivative of the denominator is minus sine theta. Did I write it here? Here it is. There it is, minus sine theta. So this is minus sine theta, and then multiplied by the numerator, which is sine theta, and all over the square of the denominator. This here means basically cos all squared. So this is cos squared theta. Now let's look at this. What is this? That is exactly cos squared theta. And minus times minus is positive. What is sine times sine? This is exactly sine squared theta. All over what? Cos squared theta. What did we say? Sine squared plus cos squared equals 1. Check this out. We've explained that. Let me just go back and show you. We showed you that sine squared plus cos squared equals 1. Here it is. Sine squared plus cos squared equals 1. Right. So, and I also showed you that sec is actually 1 over cosine. Just keep that in mind. So now, if you look at this, expression here, I want to keep page 7 there clearly seen. Right. I think it can be seen. Yeah, it can. So let me just move back a little bit like that, right? So I'm basically saying that expression there might simplify to 1 all over cos squared theta. But what is cos theta? If you look at this, 1 over cos theta is actually sec theta. So this basically is sec squared theta. So we now have established that the derivative of tangent, right, with respect to theta is actually equal to, if I say d with respect to theta of tangent is actually equal to sec squared theta, right? Don't forget this. And if you treat theta as a constant, we're going to say sec squared theta d theta, right? If you treat theta as a constant, you're going to say sec squared theta d theta. But derivative of secant of tangent, remember I'm not saying theta, derivative of tangent. Remember now we have tangent and then we have theta. Suppose theta is a function. Then you would be required to say d theta here. Theta is a function. So notice if, for example, we say tan x, what is derivative of this with respect to x? This derivative of tangent with respect, derivative of tangent first, because here we have tangent and then we have x, tan of x. Derivative of tangent is sec squared. And of course, we're dealing with x, and then differentiate x by chain rule. What is derivative of x? 1. And then when you multiply this, you just get sec squared theta, sec squared x, sorry. And that would be your derivative of tangent x. But theta will sometimes be a function as well, as you will see shortly. So now we have established that the derivative of tangent, there it is actually sec squared. And I also want to remind you that we said, and now that should take me to another item. We said here, let me just bring it up, kind of taking too long, but yeah, we'll try. So look at this. If I move this one up like this, right, look at this. We're saying sine squared plus cos squared equals 1. Now I want to do something to this function here. Rewrite it and do something to it. So check this out. What happens if I say sine squared theta plus cos squared theta equals 1? This is what we just proved. And now I want to divide throughout by cos squared theta. I'm going to have sine squared theta over cos squared theta plus cos squared theta over cos squared theta, assuming cosine is not equal to 0, 1 over cos squared theta. What is this? You agree with me that that's tan squared theta. What is this? 1 is equal to sec squared theta. So now we've established another point here. Let me call this, I don't have to give it any number, but I'm basically saying, so now what we're saying here is, take note, we are saying tan squared theta plus 1 is actually equal to sec squared theta. So this is very critical, especially if you look at this format here, this part here. If you look at this part here. So whenever I see 1 plus x squared, it should remind me of this 1 plus x squared there. And I know that therefore I can use tangent substitution. Let's just look at one example here. Here's our first integral, right there. Integrate 1 over 1 plus x squared dx. How do we integrate this? If you allow me to write it starting from here on this same page here, I'm going to say at this point, remember I told you, here is a page. I told you that whenever you see this, the tangent substitution is 1 plus x squared, or whatever number plus x squared. And it's very critical here for you to notice that 1 plus x squared has no factors. I'm going to repeat that. 1 plus x squared has no factors. And in the numerator, you don't have x. So there's nothing else you can do here other than trig substitution. So now we're going to say, let tan theta be equal to x. And then remember I told you we're going to differentiate both sides. What is derivative of tangent? It's sec squared theta, and we're going to say d theta. And on the right, dx. There you have it. So dx has been taken care of by that. And I can have here, put tan squared theta there. So now this integral then changes to the integral of 1 all over 1 plus, notice this, tan squared, because x is now tan theta. So it's going to be tan squared theta in the denominator times, remember dx is actually sec squared theta d theta. Now, what is 1 plus tan squared theta? Here it is. What is 1 plus tan squared theta? Sec squared theta. There it is. Sec squared theta. So it means the denominator now, the whole of this becomes sec squared theta. So we're moving on to our next page now. We are saying basically that, can you see it there? No, let me move it down like this. All right, so we're now basically saying this is equal to the integral of, let me bring this at the top there, sec squared theta d theta all over 1 plus tan squared. I told you it's sec squared theta. Notice this cancel. So what do I have? The integral of d theta. Remember there's 1 here. So we're integrating 1 with respect to theta. Obviously, you'll agree with me that the answer is theta. But theta is not our original variable. What is our original variable? X. So we're moving back to the connection between x and theta. There it is. We have to solve for theta here. It's going to be tan inverse of x, or arctan of x. So this, of course, we're dealing with indefinite integral. We must say plus c, and therefore this is just arctan or tan inverse of x and then plus c as our final solution. Right. Let me just do one more, and then we can close this video. I can stop this video for today. Let me just do one more. Example number 2, let's call it. Number 2, suppose I have, it says here, integrate the integral of, let's say, I can have 2 all over, let's say in the denominator, I'm going to have 3 plus x squared dx. Now you see, we have 2 problems here, at least one problem, this one here. Remember, the tan substitution, there has to be a 1 here, but there's a 3. So I'm going to make sure that there's a 1 here in that place. So now, our solution then will be as follows. I'm going to say the integral of 2 all over 3 plus x squared dx simplifies to, the first thing I take the 2 out because it's a constant, 1 all over, watch what I'm going to do here now. I factorize this out. My common factor, I force it to be 3. I force it to be 3. And I say open brackets. What is 3 into 3? 1. There is my 1. And then I divide 3 into x squared. So this is going to be plus x squared over 3, like this. Don't forget to say dx. Right. Now I can take 3 out. Remember, 3 is dividing. So this is now going to be 2 over 3. And then the integral of 1 all over 1 plus, and I have x squared here all over 3. And I have dx. Now remember here, the whole of this place must be something squared. it means I'm going to have to take square root of 3 and square it. Now that's a moment of brilliance right there. All right, let me move to the next page. So I'm basically saying, on the next page, I'm basically saying, watch how I'm going to transform that so that it complies with what we know. I'm going to transform that and say, this one here is exactly the same as, watch this, is exactly the same as 2 over 3, the integral of 1 all over 1 plus, check this, x all over square root of 3, and I say the whole of this must be squared, and then I said dx. Now you see I haven't changed anything, because if you remove the brackets, it's going to be x squared, and root 3 squared is actually 3. Now I have reached the point of tan substitution. Now I'm going to say let tan theta be equal to, notice this, x over root 3. That one there, that must be tan theta. And differentiating both sides, remember this is a constant. And there I'm just going to have this constant 1 over root 3 times dx. On the left, I'm going to have sec. This implies sec squared theta d theta is equal to 1 over root 3 dx multiplied by root 3 both sides. This is going to be root 3 sec squared theta d theta equals dx. Now I at least have that taken care of, Now I can go ahead and do tan substitution. So let me go to this page here, and I'm going to say, now watch, I'm going to say my integral now, this integral, that is going to be root 3 sec squared theta d theta there. Here I'm going to have tan, and it will be tan squared theta, and then 1 over 1 plus tan squared theta, and then I have 2 over 3 outside. So what am I saying? I'm saying you have that integral there is the same as 2 over 3, and then I'm going to say, check this out, 1 over 1 plus tan squared theta, and up here I'm going to have, remember, root 3 sec squared theta d theta, like that. And if I bring this one up there, I'm going to say this is the same as 2 over 3, the integral of square root of 3 sec squared theta d theta all over this 1 plus tan squared theta. I've just proved to you a couple of minutes ago that this is just sec squared theta, and these can cancel. And I take root 3 outside, so I'm going to have 2 root 3 all over 3. And what do I have? The integral of, remember, 1 d theta. And what is this? This is 2 root 3 over 3 theta, of course, plus a constant. I must find the value of theta. I'm coming back to where? To here. To find theta, I'm going to take tan inverse both sides, because this is, remember, theta there. Sorry, my marker is a bit too dark, but I hope you can see it there. So I'm going to take tan inverse both sides, and I get theta equals tan inverse of x over root 3. So basically, my final solution then changes to, this marker is a little bit hectic here. All right, so my final solution then changes to, may have to change this marker in my next video. So my final solution then changes to, just get that page there. Come on, just a minute. Yeah, here we go. And we just told you that this is our final solution, but this must go. And to get rid of this, we must go back to the connection between tangent there. We must go back there and say theta is tan inverse of x over root 3. So this changes therefore 2 as a final solution, 2 root 3 over 3, and then tan inverse of x over root 3, and then plus c. This is the final solution to our integral right there. Right, I am going to stop here for now. I hope you found this video useful. If you are new to this channel, please support us by subscribing, inviting friends to subscribe, liking these videos and sharing them. It will help us build the channel and then be able to produce many more videos. I am coming back with a couple more videos on tan substitution, as well as other trig expression like the sine substitution and so on. Right, I'll see you next time.